This is a reminder class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please do not share personal information during the class session for your own security reasons. All right, so we have the ticket in the chat box for you because you are in the live class. Remember, if you are ever watching the recording, you won't be able to get that password. It's only provided in the live class, and it's 10% of your grade to actually attend your classes. We only have 15 days left of the quarter. It's ending very quickly. So we can see we're already in week 7, right? So we have week 7, week 8, week 9, and then we're completely over, and classes are done. You won't be able to turn in any work after that moment, right? So no more late work after the last day of the quarter. It's not like we have a second quarter of this class. It's completely over, and then we start new classes. Okay, so today we are starting Unit 7. We're talking about the properties of waves. We'll talk about some different types of waves tomorrow. Wednesday we do have a waves lab. It's a really easy lab, so we'll knock that one out of the park. Thursday we'll talk a little bit about sound, because sound is a type of wave, so we'll talk about how that applies. And then Friday we have an extra credit game day. Hopefully on Friday my technology is working so that we can get that game actually working a little bit better. But you guys did really well last week as well, so I'm very proud of you for persevering through difficult technology problems. Okay, so we're talking about waves. We're going to look at the properties of waves, the effects of waves, different kinds of waves and factors that can influence them. We will define frequency, wavelength, and pitch, and we'll also learn about what the Doppler effect is, which you might have heard this at some point in your scientific career, but we'll learn a little bit more about how it works. So today we're going to talk about the difference between mechanical and electromagnetic waves, and then we're going to talk about the properties of waves. So we'll talk about crest, trough, amplitude, wavelength, period, and frequency. So these are 6 big words that we need to understand by the end of the class today. So waves, right? Their purpose is to transmit energy, and when we talk about mechanical waves, we're going to talk about transverse, surface, and longitudinal waves. So we'll dig a little bit deeper into that next class, but we're going to introduce them today. So first and foremost, the most important thing is that the purpose of waves is to transfer or transmit energy. They move energy from one spot to another spot. They're divided into 2 groups. The first group requires a medium, meaning it requires matter or atoms or molecules or particles. So these are what are called mechanical waves. They require a medium like water, air, other gases, solid materials. No worries, Libby, just go ahead and save the password and then take a picture of the answers so that you have them for when it does begin working. Okay, if it's still not working in like 20 minutes, let me know and email me, and I can try to troubleshoot it that way, okay? All right, good. So the other type of wave, though, does not require a medium, which means that it can actually travel through a vacuum or a area where there is no matter, such as outer space, for example. Remember that there's nothing in outer space. There's no air, right? There's no water, right? If we're talking about like outer space, not like close to the Earth. But if we go past the Earth's atmosphere into outer space, there's no matter there. But somehow, right? The sunlight can still reach us, and sunlight is a type of wave, but because it does not require a medium, it's called an electromagnetic wave. Smiley faces if this makes sense. Mechanical waves require matter. Electromagnetic waves, like sunlight, do not, and their purpose for both of them is to transfer energy. Excellent. This is number 1 in your ticket. Give me a green check when you have it saved. It's a super fast one, so I'm going to give you 25 seconds. Ready, set, go. I'm sorry, did I mix those up? I might have put it in the wrong order. Is there one that says waves transfer? Let me double check that, guys. I'm so sorry. I must have put those incorrectly. Hold on. We are on October 8th. Oh, it's the last one. Okay, sorry about that, guys. It's question number 5. My bad. Question number 5. Sorry, I must have not reordered them. Sorry, this is question number 5. Once more, go ahead, take 25 seconds, fill that in. Thank you for finding that, Vega. All right, green checks when you have number 5 saved. Looking good, just waiting on Adrian, Annalise, Ariana, Audrey, Brianna, Dalen, Edgar. Green checks, please. Haley, Jacob, Michael, Vega, and Zoe O. Green checks if we have number 5 answered. Again, it is out of order, so this one should actually be number 5. Looking good. All right, let's go ahead and move on. All right, so let's make sure we understand these terms. Go ahead, grab your whiteboard tools. You're going to match these up. You will have more than one definition for the terms, and some of these you might actually match up with both of these. So go ahead, grab your whiteboard tools, match these up. Tell me which ones do not require a medium, which ones transfer energy, which ones do require a medium like air or water, and which ones can move through the vacuum like outer space. Go ahead, get that up there, please. Looking good, just waiting on a few more answers. Get those up there. 5 seconds left. 5, 4, 3, 2, and 1. Pausing your tools. All right, I'm going to go ahead, grab my red tool here. Let's make sure we've got this. All right, looking good. So, oops, I forgot to shrink them. Sorry, let me shrink these down a little bit. So yes, we do have a couple of these that have multiple answers. Let's make sure these make sense. So, mechanical waves, yes, they do transfer energy and they do require a medium like air or water. Electromagnetic waves do not require a medium and they can move through a vacuum like outer space. However, there is one that you got incorrect. It's kind of a trick one. Remember, guys, is sunlight a type of energy? Is light a type of energy? We just talked about this last unit, 2 units ago. Is light a type of energy? Does light give you energy? Does light give plants energy? Right? Sunlight is actually the basis of our entire existence, because if sunlight did not have energy, then plants could not get energy, and then animals that eat the plants couldn't get energy, and then we that eat both plants and animals could not get energy. So yes, sunlight is energy, right? Sunlight is energy. So that being said, which one does this also need to be matched up to? Which one does this one also need to be matched up to? All waves, no matter what type of the wave they are, do this. This is the main property of waves, is that all waves do what? It was our very first question today. Yes, all waves transfer energy. All waves transfer energy. Yeah, exactly, Andre. So if we ever run out of sunlight, when the sun dies, that means that all the things that rely on sunlight will also die out. It's not going to happen for a very, very long time, though. Smiley faces, though, if this makes sense, guys, that mechanical waves and electromagnetic waves should both be matched up with transfer energy, because all waves, no matter what type of wave they are, their purpose is to transfer energy. Looking good. All right, let's keep on going. So I'm going to go ahead and share a video with you of a stadium wave, and I want you to tell me some observations of what you see going on. So let me go ahead and grab this. I'm going to copy this. All right, so it's in the chat box. I'm also going to put it on the whiteboard. It's only a few seconds long, so give me a green check when you finish watching it. Go ahead and watch it now. All right, give me a green check if you are able to watch that. Again, it's either in the chat box or on the whiteboard. You can watch it either place, but tell me, what did you see each person doing in the stadium wave? Tell me, what are some observations? Oh, I'm sorry, it was loud. Yes, definitely turn the volume down if you need to. What did we observe happening, guys? Okay, so we saw people standing up. Were they all standing up at the same exact time? Like, did the entire stadium stand up at the same exact time? No, what was happening? Tell me, explain to me what was happening. Why did it look like a wave? Why did it look like a wave? It's called the stadium wave for a reason. Yeah, so as they went around, right, different sections of the stadium were standing up at different times, right? So we saw that they didn't all just stand up at once, right? Certain ones stood up in one column, and then the next column, and then the next column, and the next column. Smiley faces if you observe that. Smiley faces if you observe that. Awesome. Okay, now the next thing I want you guys to notice is, did the people move in the same direction of the wave, right? So the wave went around the stadium. Were people actually moving around the stadium? Like, did one person start in a spot and then run around with the wave to get to the other side of the stadium? Is that something that happened? No, right? They all just stayed in their seats. Smiley faces if that makes sense. In the wave, they all just stayed in their own seats. Okay, it wasn't like they were running around to make the wave happen. Smiley faces, awesome. Thank you, Libby. I see your smiley face. Thank you, Sally. Looking good. Smiley faces if that makes sense. Awesome. Good, good, good. All right, so here's the thing. Mechanical waves, just like a stadium wave, which we just observed, they do not actually move the matter. They did not actually move the people from one spot to another spot. They didn't actually change their seats, right? They all just stayed in their own seats. Okay, so that's really important here, that with any type of wave, whether it's a stadium wave, a water wave, a sound wave, a light wave, sorry, not a light waves don't use mediums, but no matter what type of wave it is, the wave is not going to actually move particles from one spot to another spot. So the medium, the particles might move up or down, or they might kind of shake back and forth, but they're not actually going to travel with the wave. One person is not going to actually move and run with the wave. Smiley faces if that makes sense. The particles actually stay in their seats. They always stay in their seats. They might go up and down, they might wiggle back and forth, but they're not moving from their seats. Okay, excellent. So we can see here a couple examples that we'll be looking at are going to be longitudinal and transverse waves. So we can see this with this coil here, right? Longitudinal waves, the energy is going to the right, but these coils aren't actually being transported to the right. The coils are just shaking back and forth, left and right. Okay, so we can see this right here. These are just actually kind of shaking back and forth, left and right. And same thing with this. A transverse wave goes up and down. So the energy is going to the right, but the particles in the coil are actually just moving up and down. The actual physical matter is not moving. It is staying in its own seat. Okay, so as energy is transported, those coils always go back to their original spot. They always sit back down in their seat. Smiley faces if that makes sense. Smiley face if that makes sense. Excellent. Okay, so let me go ahead. I'm going to show you an example of this really quick. All right, smiley faces if you can see this on the whiteboard. Smiley faces if you can see this on the whiteboard. Awesome. Okay, so what I want you guys to notice is those two yellow dots. As the wave is moving from left to right, does the yellow dot actually travel all the way from the left side to the right side? Does the yellow dot travel to the end of the wave? No, exactly. Again, I'm just proving to you that that yellow dot, it's staying in its own spot, right? It's kind of going in a circular motion, but it's not actually moving away from its spot. It stays in its spot. Give me a thumbs up if that makes a little bit more sense now that you've seen it multiple ways. Thumbs up if that makes more sense. The particles, the matter does not actually move. Excellent, looking good. I know, it's pretty cool to watch, right? All right, guys, this is number 1 in your ticket. Go ahead, give me a green check when you have it saved. Matter is the first blank and energy is the second blank. I'm going to go ahead and give you 40 seconds. When you have that done, give me a green check, please. All right, waiting on a green check from Andrew, Andrew, Annalise, Sienna, Ciara, Haley, Jacob, Johnny, and Ty. Green checks when we have number 1 saved. Again, I'm so sorry that first question we went over was actually out of order, so now all of these are going to be a little bit out of order. Looking good. All right, guys. So, remember, mechanical waves, remember the matter itself stays in place, but technically mechanical waves, we do say that they're moving in the direction of the energy, right? So the actual wave is moving in the direction of the energy, even though the matter itself physically is staying in place. And again, there are going to be 3 types of mechanical waves that we're going to look at. Transverse waves, which move up and down, those are the ones that we're pretty familiar with, right? They look like this. So transverse waves move up and down. But there are also longitudinal waves. For example, sound waves are longitudinal waves where they actually just push molecules back and forth. So their molecules actually move left and right, pushing the next molecule next to it. Yes, this will be number 2, correct. And then the last type, we just saw a GIF of it. That was what I just showed you. That was a surface wave where the surface of it actually moves in a circle. So we'll take a look at those ones tomorrow a little bit more, but this is just an introduction. Again, these are mechanical waves, which means that they do require matter. Okay, so they do require matter. So transverse waves are things like strings. Longitudinal waves are things like sound moving through air. Air is matter. And surface waves are things like earthquakes. So the ground is a type of matter, or water. So water is the matter. Okay, so go ahead, give me a green check when you have number 2 saved. This is number 2 in your ticket. I'm going to go ahead and give you 30 seconds. Green checks when you have it saved. All right, it's Andrew S., Eric, Haley, Jacob, Johnny, green checks please. Tyson, I'll go back to it a little bit later. All right, I don't give the answers out during the class just because I want you to be able to see the actual slide, all right? It'll also be in the recording later, so that's also an option. Excellent, guys. All right, let's keep on moving. So let's go ahead and talk about the actual properties of waves. So we're going to learn a whole bunch of terms here. So the first 2 terms that we need to learn are crest and trough. So crest and trough are the opposites of each other. So crests are going to be the highest point on a wave. So the long definition is it's the point on a medium that demonstrates the maximum upward displacement from the equilibrium being the center. So the maximum upward displacement just means the highest point. Smiley faces if that makes sense. You can see it pointing to the crests here. Crests are the highest point. Just like you think about like the crest of a water wave, right? That's going to be the highest point. The trough, on the other hand, if you think about a trough, like a horse trough, a trough is something that has a dip in it, right? It's like a giant bowl for water for a horse, right? So just like that, think about a trough being able to actually hold water in it. Okay, that might help you better be able to remember that the trough is the one on the bottom. So again, the long definition is it's a point on the medium that demonstrates the maximum downward displacement from the equilibrium, the midpoint. In other words, we can call it the lowest point on the wave. Smiley faces if that makes sense. Highest point is at the top, called the crest. Lowest point at the bottom is called the trough. And the very center is called the equilibrium. The halfway point between the top and the bottom is called the equilibrium. Excellent. Let's make sure that this makes sense. I'm going to give you your polling tools really quickly. A through C. A is the top, B is the middle, C is the bottom. Which of the following is the equilibrium? A, B, or C? Which of the following is the equilibrium? Come on, let's do this. We should know this. Think about the word equilibrium. Literally has the word equal in it. What does that make you think of? Awesome. Seeing lots of answers. Looking good, looking good. Yes, this one is going to be letter B. B is the equilibrium because it is the very center. Excellent. All right, the next one. Which of these is the crest? Which one is the crest? A or C? A or C, the top or the bottom? Which one is going to be the crest? Go ahead and get me your answer here. Use your polling tools. Polling tools. Adrian, Andres, Andrew, Annalise, Audrey, Sienna, Ciara, Dalen, Eric, Haley, Jacob, Johnny, Kim, use your polling tools, Siva, Ty, Zoe O, and Zoe P. Which of these is the crest? A or C? A or C? Libby, please do not put answers in the chat box. Thank you. Excellent, looking good. So yes, this one is going to be A. This is the crest. Crest is always the top of a wave. Exactly, the highest point of a wave. Which of the following is the trough? Which of the following is the trough? This one should be easy. Process of elimination. What's left over? Which one is going to be the trough? Again, if you think about it like a horse trough, right? A horse trough literally has a dip in it that holds water, right? So think about what a horse trough looks like and find that on this diagram. Yes, this one is definitely going to be C, right? This right here is the trough. Smiley faces if you feel good about that. Smiley faces if you feel good about that. Equilibrium, crest, and trough. Excellent, looking good. All right, so those are our first 2 terms. Now for the next 2, okay? So amplitude is going to be the actual height, right? So what we just learned about is we learned about what the top point and the bottom point are called, but those don't give us actual measurements. The amplitude, though, does give us a measurement. So amplitude we would actually measure in like meters or centimeters or inches, etc. Smiley faces if that makes sense. Crest and trough are just points. They don't have actual measurements. Amplitude does. So that being said, the amplitude is going to be the height, how high it is, either from the rest to the crest, okay, rest being the equilibrium. Okay, so equilibrium can also be called the rest. So rest to crest, or the height of the hill, that's the amplitude. Or you could also measure it the opposite way, because what you'll notice is that the top and the bottom actually have the same height. They are symmetrical in that sense, right? So we can see the top and the bottom look very similar to each other. So you could also call it the rest to the trough. That height, that distance, is the amplitude. Smiley faces if that makes sense. So the height of the hill or the depth of the valley, they're equal to each other. Okay, these two numbers are equal. They're the same exact thing. You can measure amplitude either way. Now, that being said, when we talk about amplitude, for example, when we talk about sound, the greater your amplitude is, the more energy you have. So if you think about like decibels, decibel is telling you that you have a really big amplitude. So for example, like a vacuum, if a vacuum has 100 decibels, then it's going to be a very, very loud sound compared to something that is only 20 decibels. Smiley faces if that makes sense. Greater amplitude means more energy, and in the case of sound, that means more sound. In the case of water, that means a much more powerful wave or a much more powerful earthquake, so on and so forth. Awesome. Now, the next thing that we need to talk about is wavelength. And the reason we have a length of a wave is because waves actually repeat. If you've ever seen a wave, you see that it's very rhythmic, right? So waves repeat in a cycle, and the length of one wave is going to be called the wavelength. So wavelength is the length of one of the complete wave cycles. So this could be from crest to crest or from trough to trough, right? And again, it's a length. So this is also being measured in things like meters, centimeters, inches, etc. Okay, they're actual distances. And we can see this here, right? If you start at the top of a wave to complete a cycle, you need to go down and then go back up until you hit that point again. Smiley faces if this makes sense. This is why this right here is a wavelength. Crest to crest is a wavelength. Because you start at a crest, you end at a crest. Same thing with troughs, right? You can start at a trough, follow all the way through, and keep on going until you hit another trough. And this would also be a wavelength. There is actually one more way that you could actually measure this, and the way that you can measure this is starting at the equilibrium. Okay. However, this is really important. If we start at the equilibrium, you have to measure until you hit going the same direction across the equilibrium. So we start, for example, going down the equilibrium. I'm going to follow it through. Okay, so I'm going to follow it through. And right here, I hit the equilibrium again, but am I going the same direction this time? If I'm following this equilibrium, am I going the same direction? Tell me in the chat box. Am I going the same direction across the equilibrium as I follow this? Watch my cursor here. I started by going down, and now I'm going which way? Is it the same way? Am I still going down across the equilibrium when I cross it here? No, I'm going up across the equilibrium now. You can see as I trace this, I'm actually going up across the equilibrium. Smiley faces if that makes sense. As I'm following this, I'm actually going up the equilibrium. So this does not count as a full cycle. This does not count as a full cycle because I have to keep on going until I cross the equilibrium the same way. So I'm going to keep on going until I hit the equilibrium again. And this time, am I moving the correct way? Am I moving the correct way? I started by going down. Here I went up, and here what's happening? Am I going the right way this time? Yes, so this right here would actually be another example of a wavelength. When we go down across the equilibrium, all the way to when we go down across the equilibrium again. Smiley faces if that makes sense. That's another way to measure wavelength. Basically, the best way to think about it when you're thinking about it this way is you need two humps. All right, you need the bottom hump and the top hump. Okay, so that's a good way to remember that as well. Excellent. All right, let's keep on moving. So that being said, A, B, C, or D, let me give you your polling tools. Which of these is the amplitude? The amplitude. Remember, both of these have to actually be measurements. Not just points on the waves. They are not just points on the waves. Okay, so for example, A and D are just points on the waves. Right? These are just showing you points. We need actual measurements, distances. So which of these shows the amplitude? Look for distances, not just points. Looking good. Get me answers. Still waiting on a ton of participation. Wake up, guys. Come on, the faster participation, the faster we can end class. I can make sure you get to your next class on time. Or if you don't have another class, you get to end a little bit early, but I need your participation. All right, Andrew, Angelina, Annalise, get me your answer, please. No problem, Haley. Thanks for letting me know. Sienna, Ciara, Dalen, Eric, Jacob, Johnny, Michael, Tyson, and Zoe O. Let's get me those answers. Looking good. All right, so yes, this right here is the actual amplitude, right? So B is going to actually be the amplitude, okay? Because it's a height, it's actually a measurement. Good. Thanks for letting me know, Brianna. All right, cool. Now, what about the wavelength? Which one is the wavelength? Tell me using the polling tools, which one is going to be the wavelength? Again, wavelength is also a measurement. Wavelength is also measured in meters, centimeters, inches, so on and so forth. The length of a wave, literally the length of a wave. All right, getting some answers. I have 10 answers now. Keep working. Looking good. Waiting on Andrew, Angelina, Annalise, Brianna, Ciara, Dalen, Eric, Haley, Johnny. Looking good. All right, guys. Yes, this one is going to be C, right? So C is definitely our wavelength, right? It's the length from one point to an identical point, right? So from trough to trough. We could also say crest to crest, or equilibrium to the same equilibrium. Okay, excellent. So that being said, guys, again, what is A called? What's the point A called? Right? What is the very tippy top of a wave called? What's the very tippy top of a wave called? Yes, Edgar, yes, this one is the crest. What about the very bottom? Think about a horse drinking water. What's the very bottom part called? If the tippy top is the crest, what's the bottom? Yes, you've got it, Audrey. This one is the trough. But again, crest and trough just tell us what points they are. They are not actual measurements. Perfect. Okay, so the last two that we need to talk about, the last two definitions are period and frequency. So period is the time it takes for a single wave cycle to occur. Okay, so this is the amount of time it takes for just one little cycle from crest to crest, trough to trough, or equilibrium to occur, right? You see a top hump and a bottom hump. So, if you want to think of the best way to remember this, because period and frequency sound similar, think about it as being a period of time. So you need a period of time for how long it takes for a single wave to occur. Smiley faces if that makes sense. A period of time for how long it takes for a single wavelength to occur. Excellent. Now, frequency is actually the opposite. Frequency is the number of cycles that you get in 1 second, right? So period is time for a single cycle. Frequency is cycles in a single second. Okay, so another way to think about it is how frequently do the cycles occur? You should end up with a number of how frequently the cycles occur. So a period will give you a time in like seconds. Okay, a frequency is going to give you an actual number of cycles. So 2 cycles in 1 second, for example. It is not the same as period. Again, frequency tells you how often the wave cycle happens. Period just tells you the time it takes for a single wave. So for example, you can see right here, you can see right here, we've got 1 second, and in that 1 second, there are 3 waves, right? 1, 2, 3. And so the frequency for 1 second is 3 waves. Smiley faces if that makes sense. There are 3 waves or 3 cycles in this 1 second. So that's our frequency. So our frequency is 3 cycles in 1 second. Smiley faces? I didn't get a lot of smiley faces. Need some smiley faces if that makes sense, please. Perfect, looking good. Now, the period, on the other hand, is just the time for a single one of these cycles. So what do you guys think? How long does it take for just one of these cycles to occur? If 3 of them take 1 second, how long do you guys think would just one of them take? How long do you guys would think just one of them would take? Think about dividing this 1 second into 3 parts. How long are each of these taking if they add up to 1 second? Do we know? What would be 1 second divided among 3 cycles? What's 1 divided by 3? What's 1 divided by 3? We should have a calculator out if we don't know for sure. We need to get a calculator out if we don't know. This is actually mental math, guys. We should already know this, but if we don't, we need a calculator out. What's 1 divided by 3? Nope, that would be the opposite. Put 1 in first and then divide by 3. Use the calculator. Let's go, everyone. Come on. Grab your calculators. Let's get an answer here. Work together. Work together. Yeah, 0.333. Yeah, exactly. Right? So if you look at this, right, what we actually have is for a single cycle, it takes 0.333 seconds. Right? Here, this one will take 0.333 seconds. And here, this one will take 0.33 seconds. So that would be the actual period. 0.33 seconds is how long it takes for a single one of these periods. Put 3 of them together, and you suddenly get your frequency. Smiley faces if that makes sense. Okay? So our frequency tells us how many are in 1 second. Our period tells us how long it takes just for one cycle. Excellent. Okay, so I know that can be a little bit confusing. It's one of the hardest concepts. So I'm going to go ahead and I want us to take a look at a high frequency versus a low frequency wave. Okay, both of these take 1 second. So first, let's figure out the frequency for the high frequency one, the number of waves in 1 second. So take a look at this, guys, right? So we can see 1 wave, 2 waves, 3 waves, and 4. So here, this would be 4 cycles in 1 second. Smiley faces if that makes sense. The frequency here is 4 cycles in 1 second. Okay, because we had up, down, up, down, up, down, up, down 4 times. What about down here, guys? What do you guys think would be the frequency for this one down here, for our low frequency wave? Up, down, up, down. How many cycles do we have? How many complete cycles do we have in 1 second? Tell me in the chat box. You saw 4 up downs here. How many do we see down here? Count them up. Up, down, up, down. I got an answer from Sally. I see Jeremy typing. How many cycles do you see here? Up, down, up, down. Michael, Ariana, thank you. Yeah, you should see 2 of them, right? So here's 1 cycle, here's 2 cycles. So the frequency here is that there are 2 cycles in 1 second. Excellent. Okay, what about the period? So we want to think about the time it would take for a single wave, right? So again, we need to take this 1 second and divide it among 4 different waves, right? We need each wave to take an equal amount of time and in total equal 1 second. So tell me, what would 1 divided by 4 be? What would 1 divided by 4 be? Otherwise known as a quarter. What's 1 divided by 4? Yes, exactly. So the period here would actually be 0.25 seconds. So the amount of time it takes for 1 cycle here would be 0.25 seconds, or our period. Smiley faces if that makes sense. Remember, period gives us an actual time, a period of time, an actual period of time. Excellent. What about our low frequency one? Take a look at this one here. We have 2 waves that in total need to take 1 second. So what would it be if I divided 1 divided by our 2 waves? What is 1 divided by 2 equal? Otherwise known as a half. What would be our period if we had to have 2 waves in 1 second? How long does it take for just one of those? 1 divided by 2, what does that give me? Yeah, exactly. It's going to give me a period of 0.5 seconds because this means that for a single wave, it only takes me 0.5 seconds. Smiley faces if that makes a little bit more sense now. The difference between the frequency and the period. So again, frequency gives us a number of cycles in a single second. Period gives us a period of time for 1 wave. Okay, awesome. Let's make sure that this makes sense. Grab your whiteboard tools, match these up, please. Right, we know the height from rest to crest. Right, what is that? We know the length from crest to crest or trough to trough from one point to a similar point. We know the time for 1 single cycle and the number of cycles in 1 second. Go ahead, match these up, please. Go ahead, do that on the whiteboard. Yes, this is going to be question number 3. Work, work, work. Let's go. Oh, I can't even trick you guys. You guys got that so easily. I love it. That's what I like to see. It means we really know it. Okay, I'm going to pause. 3, 2, 1. And I don't even feel like I need to really correct this. I'll still do it. I'll still put the red up there, but I feel like you guys got this. So yes, amplitude is going to be the height from rest to crest or rest to trough. The frequency is the number of cycles in 1 second. Period is the period of time for 1 cycle. And wavelength is the length from one point to an identical point. Excellent. This is number 3. Give me a green check when you have number 3 saved. I'm going to go ahead and give you 40 seconds. Green checks, please. Work quickly. 20 seconds left. Green checks all around, please. 5 seconds. All right, Adrian, make sure I get your green check. Andrew, you as well. Brianna, Dalen, Eric, Jeremy, Kim, thank you. Tyson, thank you. Give me your green check. Looking good. All right, so today we talked about the difference between mechanical or waves that require mediums and electromagnetic, waves that don't require mediums. And we also learned these 6 terms: crest, trough, amplitude, wavelength, period, and frequency. Give me a smiley face if you feel good about these. They're all similar terms, which is why they're a little bit hard to go over, but I feel like you guys got it successfully. Excellent. Okay, guys. Make sure you have your tickets saved. I'm going to send you the quiz link. I want you to open up the quiz right now. Do it with your ticket because all the answers are in your ticket. And then when you're done with it, submit both of them. All right, here's your last word, and I will see you all later. This is number 4. See you guys later. Bye, everyone.